Good morning. Welcome to the first session on zeolites. I'm Mark Davis from Caltech, and I'll be one of the session co-chairmen. My other co-chairman is Dr. Henson from Eindhoven. So in this session this morning, we have one keynote lecture and then 5 presentations. And so let's just get right to it and start with the keynote lecture. Alex, will you come up and begin? So our keynote lecturer in the area is Alex Bell.
So thank you, Mark. It's a pleasure to be here. It's first of all my responsibility and duty to thank Umit Özkan for inviting me to give this keynote. Thank her and the other members of the organizing committee for this opportunity. It's also appropriate that this session on catalyst design begins with a talk, actually a series of talks on zeolites. And to motivate that for you, I just remind you here with this first slide that zeolites find extremely broad application. Everything from the conversion of petroleum to lubricants and transportation fuels, the synthesis of chemicals, organic chemicals, specialty chemicals, and then finally for the abatement of NOx in automotive converters. And what makes these materials so fascinating is their structure. So we know that they're crystalline, largely crystalline to begin with. You can see that on the side over here. And then if we look in the electron microscope, whoops, do that again. If you look in the electron microscope, what you see is an internal structure which is highly porous on the dimensions of nanometers, size of molecules. And then if you look very closely at the walls, you'll see where the aluminum is substituting for the silicon. And then the charge compensation is either by a proton, in which case we have a very acidic material, or we can replace that proton with a metal cation, either monovalent or divalent. So the activity and selectivity of these catalysts depends on what we have at the charge compensating cation site. But what is more and more intriguing is that the size and shape of the cavity in which this active center sits also has a role in defining activity and selectivity. And I'm going to illustrate that for you with a series of 3 examples here. We'll talk first about the oligomerization of propene as an example of alkene oligomerization on nickel sites in the zeolite X. And you'll notice that's the active center is the reddish colored sphere, nickel 2+. But there are a lot of other cations in the system which are not catalytically active, but as you'll see play a role in defining both the activity and selectivity of what one produces. Then we'll turn to an acidic zeolite, MFI, with a proton in it, and look at the cracking of butane. We'll learn what theory can tell us about the size and structure of transition states for both the cracking and dehydrogenation reactions. And then we'll explore some more recent results about what happens if I stay within a 10-member ring system, but I start providing more and more space within the zeolite within which to accommodate these transition states. And I'll show you that the terminal to central cracking distribution changes as well as the ratio of dehydrogenation to cracking. And then we'll finish with a topic that is of contemporary interest, which is the isomerization of glucose to fructose. And you'll see that this is a very important step in the overall processing of biomass on its way to diesel fuels and gasoline. And this will happen in tin beta. So let's start with the first example. And I'm going to motivate each one of these examples by the slide. And here I remind you that like alkenes are produced both by FCC, fluidized cat cracking, and also increasingly in Fischer-Tropsch synthesis. These are alkenes that have molecular weights between C2 and C4, maybe up to C5. These are relatively volatile compounds. They can't be blended into gasoline or diesel fuel, and therefore energy producers are very interested in taking this feedstock, not wasting it for just combustion, but oligomerizing it, turning it into materials that can be blended into the diesel feedstock in particular. And what the patent literature teaches us is various nickel catalysts are active, but there's little understanding as to why they're active, how they're active, what happens, and why do they deactivate. So my first example is going to show you what we've been able to learn about this. So the catalyst is easily prepared by taking the sodium form of X-zeolite and replacing it with nickel cations. And as I'll show you in a moment, you don't want to put too much nickel into the system because that's the cause of deactivation. And one of the things we discovered is how that deactivation occurs. So if you keep the level of exchange down below 5%, we can produce active and selective catalysts. And we have discovered that initially when you put the nickel in, it wants to sit in the hexagonal cages. So if you look at the slide, it's the 1' site where the nickel is very happy, surrounded by a lot of oxygen. But to make this catalyst active, the nickel actually has to migrate into the supercage. And we have characterized these materials by various means. We know that all the nickel is present as isolated nickel 2+ cations. There are no nickel oxide particles or other forms of nickel. So I move ahead and put this catalyst now on stream in the presence of propene. And we've seen time and time again that initially nothing happens. In fact, we were very discouraged when we first did these experiments, completely inactive catalyst. But if you're patient and wait a couple of hours, the catalyst comes up to full activity, and then it begins to deactivate. And this period of activation corresponds to the digging out of the nickel cations from the hexagonal cages and putting them into the supercages. If we have too much nickel in the supercages, they actually find each other and form a complex which is inactive, and that's the cause of the deactivation. I'll show you the mechanism in just a moment. And what we learned is that if you put less and less nickel in, it becomes more and more active. It's almost what we would call a homeopathic effect. Of course, you can't put no nickel in and have an extremely high effect, and so it dies at some point. But eventually you can make a stable catalyst, and the kinetics are first ordered in the supply of propene with an apparent activation energy of 11 kilocalories per mole. Now the interesting chemistry is shown here, it's summarized. You have several processes which lead to the removal of the nickel from the hexagonal cages. It's transferred to the surface of the supercage, and its stabilization then as a complex together with propene. And I'll show you the structure of that complex in a moment. And then you have dimerization, the reaction you'd like to carry out. And finally, deactivation, when two of these active centers, both in a supercage, find each other, and you can form a bridge between them. And that bridging structure is inactive. And this simple set of steps will very nicely describe the overall kinetics. In fact, the solid line that you see here, and we could show this same solid line from many other nickel loadings, properly describes the temporal evolution of this catalyst. Now what I want to focus on, because it's a more interesting part of the story, is the active form of the zeolite. So what we've been able to show theoretically is that if you introduce propene, the propene will ligate with the nickel cations and stabilize it in the supercage. And then you find that the resting state of the catalyst is a nickel 2+ cation surrounded by 3 propenes and 1 allyl anion. So the net charge on the bracketed quantity is +1, and there's a remaining -1 on the zeolite. And you might wonder, where is the other negative charge on the zeolite? What's compensating it? It turns out that along the way, you remove a proton from one of the propenes, and that charge compensates the second anion. So we have this nickel, 3 propenes, 1 allyl as the active component. And what we have found theoretically, is that that material will then bind a 4th propene very weakly, and then the bond CC bond formation step occurs. This is the rate limiting step. And after that, everything is strongly downhill in terms of energy until we eventually end up all the way on the right-hand side with one hexene molecule as a product in the gas phase, and we return to the resting state of the catalyst. So we start on the left with the resting state of the catalyst and two propene molecules, and we end up on the right with one hexene molecule and the resting state returned. Now what you'll notice is that the apparent activation energy here that we calculate is 12 kilocalories, so it's within a kilocalorie of what we see experimentally. We get first order kinetics consistent with experiment. We can do similar calculations for other products besides the trans-2-hexene, which is the dominant product. We can look at monobranched products. There are several variations on a theme here. The activation barrier is about 2 kilocalories per mole higher. And if we go to dibranched products, it's 5 kilocalories per mole higher. Now you might think that this is too small a change in activation energy to make a difference, but it turns out that this is exactly the activation energy difference that you need to explain the product distribution. So you see here we get 60% the 2-hexene, 35% the monobranched material shown in the middle, and only 5% dibranched. And these relatively small differences in activation energy are sufficient to account for this variation. Now, nickel is the active component, but there are a lot of other cations present in the zeolite. Remember, this is a silicon to aluminum ratio, zeolite with a silicon to aluminum ratio of slightly more than 1. And in the example I'm showing you, all of these charge compensating cations are sodiums. So the question is, do they have an effect of any kind? They're certainly not catalytically active. So what we're going to do is look at what happens if we switch sodium for lithium, or we switch sodium for divalent cations such as calcium or magnesium, and look at the consequences. So here we show on the right the cartoons. And what we're going to find is that as you substitute either monovalent or divalent cations into the lattice, the size of the lattice shrinks or expands depending on the size of the cation. And we know this from X-ray crystallography. But then you'll notice that some of these cations also occupy space in the supercage. And so intuitively you can sense already that the confinement of the nickel cation complex is going to be altered by changing the nature and composition of these non-catalytically active cations. And this intuition is then borne out by experiments, as I show you here. And we see that if we plot as a descriptor the free volume, in other words, the accessible volume inside the supercage, and then we look on the left at the rate per nickel cation, you'll see for monovalent cations, as we get smaller, there's more space inside the zeolite, and the activity goes up nearly an order of magnitude. If you switch to the divalent cations, the trend is the same, but you'll notice that you start lower, and this must be because the crystal field has changed when you use a divalent versus a monovalent cation. And this is a subject that is part of an ongoing theoretical effort that we have right now. Now there's a second consequence of changing the cation, and that is on the product distribution. So I show you in the plot the ratio of linear to dibranched material. And you see this starts with monovalent cations at about 15 excuse me, for potassium, and drops to about 10 for lithium. There's again a drop going to magnesium, and a further drop down to about 5 or so for strontium. Same thing can be seen if we were to plot the linear to monobranched material. So the thing that we learned from this first example is that, of course, the nickel cation is the critical element. The resting state is this complex that involves 3 propenes and 1 alkyl anion around it. We can explain the energetics of making the various products using this structure and the distribution of these products. If we change the cations, then we change the rate and activity of this nickel, as well as the distribution of products. And we have further ability to tune this material by changing from monovalent to divalent cations. So this is the first illustration of the fact that you have an active center, but its behavior is very much dependent on what's in the neighborhood and the size of the neighborhood. Let me switch to my second example, which concerns cracking. So if you go to low enough partial pressures of alkanes, all the reactions become monomolecular. That means they first order in the propane concentration, in this case, and you can get two reactions here, either terminal cracking to make methane and propene. We're starting with butane, so you get methane and propene. We can get central cracking and get ethane and ethene. Then you can do dehydrogenation. There are actually two pathways. I only show one here for the terminal dehydrogenation. But you could also dehydrogenate at the central CC bond and get then the 2-butene. So the questions we're going to ask is, what are the structures of the transition states for cracking and dehydrogenation? How different are they? How does the confinement affect reaction energetics? And then finally, we're going to look at the question from an experimental point of view of does confinement influence the product distribution? In other words, does the size of the neighborhood, in addition to having a proton there, influence the outcome of these reactions? And we're going to do the first part theoretically, and the model that we're using here is one in which we do quantum mechanics on a relatively small cluster. There are 5 tetrahedral atoms in it, so this is called a T5 structure. It's shown in blue on the right-hand side of the slide. And then we have to model a sufficiently large part of the rest of the zeolite to capture the effects of electrostatic and van der Waals interactions. And while I'm not going to show this, we have found through doing such calculations that you have to include of order 300 to 400 tetrahedral atoms and the associated oxygen atoms around the active site in order to get convergence towards experimental results for activation energies and heats of absorption. So this is what is called a QM-MM model, QM for quantum mechanics, MM for molecular mechanics. The MM part goes extremely rapidly, the QM goes more slowly, and this is the reason why you don't want to do all these calculations in the molecular mechanics framework. So what we discover for cracking is that the transition states are relatively early, and they're a 3-center interaction of the proton, shown as H1 there, interacting with the 2 carbons of the butane. There's about a 20% stretch in the carbon-carbon bond relative to its equilibrium value. We've estimated the entropy of activation for terminal cracking relative to the just physisorbed butane as nearly 0, so there's very little entropy change going from reactant to transition state for terminal cracking, and it's slightly negative for central cracking, -4 here. So what we're discovering here already is that there are subtle effects on the entropy of activation for the cracking. We'll come back and look at the energetics in just a moment. Now the next thing we can look at is dehydrogenation. And here there's a little more of a surprise, because what we discover is that the proton again attacks, in this case, the hydrogen of either the central bond, the CH2 group, or the CH3 group, so we get either methyl dehydrogenation or methylene dehydrogenation. But in both cases, this is a late transition state. The H2 molecule is almost completely formed. The HH distance of that molecule is almost the same as in molecular H2. And the third hydrogen, labeled here as H3, is on its way to returning towards the zeolite to provide the charge compensating proton. So this is an extremely late transition state. The charge on that H3 is nearly what it is on the Bronsted proton. And when you calculate or estimate the entropy of activation, now it's positive relative to the reactant state. And that's because this H2 is free to rotate, at least in 2 dimensions. And there's some ability to translate for the C4 fragment. I should say that these numbers that we're coming out with have also been matched in experiments. We've seen that experimentally we can get about the same entropies of activation that we see theoretically here for both the cracking and the dehydrogenation. So let's turn now to the energetics and ask, why do we have to include the effects of confinement? Why do we have to do the molecular mechanics part of the calculation, including 300 to 400 tetrahedral atoms? So what I show you here in the second column from the left are our calculations. And there are 2 sets of numbers. The first, without the parentheses, is the final answer that we get. And the one with the parentheses to the right is the number that we would get if we turned off the molecular mechanics part of the calculation. And what's very interesting is that when you do that, you get higher activation energies because you don't have the stabilization from the Coulombic and van der Waals interactions. The most important part, it turns out, is the Coulombic, because these transition states are positively charged, they're carbocations. And if we look at earlier calculations done in our group or done in China by Ding et al., you see that if you leave off the effects of the confinement, the numbers that we get are consistent with numbers that have been obtained earlier for small clusters. This is the right-handmost. And if you go towards the larger clusters, which give you partial in confinement, so a T23 cluster that we've done earlier, you move in the right direction. You're moving towards lower activation energies. Now, the real test of the quality of things is to compare to experiments. And here I show it. Of course, our silicon to aluminum ratio in the theory is infinite. In the experiments, it's closer to 40. And I've taken experiments both from our laboratory, all the way on the right, and from Cornilla and all work done in 1992 in the middle. But you'll see that for central and terminal cracking, there's generally very good agreement within a kilocalorie or so. And this agreement with experiment would not exist if we had avoided the calculation of the van der Waals and electrostatic effects. Now, if you look downwards in the table, you'll see that there are 2 numbers there theoretically for the dehydrogenation, and they span the experimental values. Now, it's not quite fair to make the comparison this way because experimentalists can't tell, looking at the results of their experiments, whether you did methyl or methylene dehydrogenation, because you only form one kind of butene. It's the 2-butene because of the 1,2 isomerization, which happens along the way as the butene is coming out of the zeolite. So it's more appropriate, actually, to take what I call a weighted average of the theoretical values. In other words, weighted according to the number of hydrogens that you have available for dehydrogenation. And now you see that the weighted average theoretical value falls in between the 2 experimental values. So this is comforting that given that there are uncertainties in the experiments and how you measure these activation energies, that at least theory and experiment are coming fairly close together. So I'd like to end this segment by asking, what if I start making the confinement bigger and bigger around the proton? So we worked so far with MFI. We're now going to look at SFV, MEL, MWW, TON, and STF. These are all designations from the International Zeolite Atlas, and the popular names are shown in parentheses. Now, these are color-coded according to the different kinds of channels and pore spaces here, just to give you kind of an easier view of how confinement is changing. But largely, as we move from the upper left-hand corner to the lower right-hand corner, we're going in the direction of more and more volume. But these are all 10-membered room channel systems. And the question we're going to ask is, does it matter whether I have a proton in MFI or STF in terms of the ratio of terminal to central cracking or dehydrogenation to cracking? And here are some very recent experimental results with these 6 zeolites. They're all color-coded here, the points. And what we find is that if you use as a descriptor the accessible volume to surface area ratio, this is a unit that has units of length. Don't pay attention to the details of the size. That's not critical here. But if you look at this descriptor, you'll find that the central to terminal cracking ratio falls from roughly 1.1 down to about 0.2, so of order 5.5-fold change, and a comparable order change in the ratio of cracking to dehydrogenation. Now, I don't have time to go into the details of what is the cause of this, but I will say that the dominant cause that we've been able to analyze so far is the effect of entropy. So as we provide more space for the slightly larger transition states for terminal cracking and for dehydrogenation, these reactions start to dominate over central cracking, and this is giving you the trend line. So the bottom line here for this story is that the transition state for cracking is early, has a negative or a slightly negative delta S event activation. The opposite is true for the transition state for dehydrogenation, positive delta S. We can replicate the experimental values of the apparent energies of activation by taking into effect the effects of confinement, and changes in that confinement can change the selectivity between cracking and dehydrogenation. So again, this is a very nice illustration of the effects of confinement. Now the last example is going to be different from the first two, and it relates to work that we're doing and others are doing on biomass conversion to diesel. So on the left, I show you that biomass is a very complex structure if you look at plant matter, but you can deconstruct it, get rid of the lignin, that's what I call the wax wrapping around the carbohydrate part, that's the cellulose and hemicellulose, and that's the part that you can then decompose further into the 2 sugars, glucose and xylose. If you're in the biotechnology sector of the biomass conversion business, you would then take these sugars and ferment them to either ethanol or butanol. If you're in the catalysis sector of the business, you might try dehydrating these materials to hydroxymethyl furfuran, or HMF for short, and xylose to furfuran. And it turns out that you can use these 2 building block molecules to build up diesel additives as well as gasoline additives. Now, one of the interesting steps is the transformation of glucose to HMF. And it turns out that that's not easy because first you have to make fructose, so it's an isomer of glucose, and then that sugar will dehydrate very readily. And our chairman, one of our chairs, Mark Davis, has done some very beautiful work in this area and demonstrated that tin cations put into the framework of beta zeolite will do this very effectively. And here I illustrate this first step, the isomerization, from glucose to fructose, and then the easy dehydration using an acid catalyst to take you to HMF. And what is rather interesting is that tin beta does this selectively. You can get up to 60% selectivity to fructose, but if you take tin oxide or just tin chloride in water, all of these reactions are carried out in water, I should say. You don't get any fructose. So we've asked the question of how does this chemistry go? And again, reading the literature that has been provided by Mark and his co-workers, particularly Yuri Roman-Leshkov, it's already been shown from experiments that the ring has to open. That's the first step. But the rate limiting step is the hydride transfer. That little hydrogen is shown in red. You'll notice it moves from the second carbon to the first at the top there. And then, of course, you have to reclose the ring to make fructose. So there's a summary of the experimental evidence, and what we want to do is model this. So we start with the structure of beta zeolite. We substitute into it this green atom, which is the tin. Here it's shown as being completely tetrahedrally bonded to oxygen, so it's a framework tin. But we know again from the Davis group work that in fact this structure isn't as active as the one in which you've broken one of the tin oxygen silicon bonds and replaced that with a silanol group on the silicon side and a tin hydroxide on the other side. So that's the structure we're going to use. And again, we're going to use our QM-MM methodology. So here, the chemistry turns out to be extremely difficult to capture. And it took us the better part of a year and a half to get this right. But I'll show it to you in 3 slides, the results of a year and a half's worth of work. So the first step is the ring opening. So we go from the top, from intermediate I1, which is the glucose absorbed from an aqueous solution. We've accounted for the effects of hydration here, theoretically, into the zeolite, which doesn't tolerate water very well. And then the steps all the way to I3, which takes us to the final state of the ring open structure. And what you'll see there, if you look carefully, is the interaction of the Lewis acid center on the tin with one of the hydroxyls on the sugar, and one of the silanol groups on the rest of the zeolite with the oxygen in the ring of the glucose. So this is a concerted push-pull kind of interaction that leads to ring opening. Now the second step, and the critical one, that is involving the isomerization or the hydride transfer of that red labeled hydrogen. You can see again this involves this pull-push kind of mechanism. So this is very much a concerted effort on the parts of 2 pieces. There are also interactions of what I call the tail of the molecule, which is pointing upwards on the screen, with the rest of the zeolite. So the confinement is very much defining how the chemistry occurs. But once you're past the isomerization step, which we calculate to be 23.4 kilocalories per mole, good comparison with Mark's value of 21.2 experimentally, the rest is fairly easy, and that's the ring closure, which I show here, to take you all the way finally to fructose, and then the fructose desorbs and comes back out into solution. So this is a slightly endothermic process, net-net, and we've been able, after a lot of effort, to capture the right chemistry, theoretically using our QM-MM methodology. Now we can do one more thing. We can explore what about other elements. And so we've looked at zirconium, tin, niobium, titanium, germanium, silicon, so that's the null case, and vanadium, in which case it's a vanadium group actually. And we see that going from left to right, we look at the bars and look at the calculations, the activation energy is increasing, not over a large range, but it increases systematically. And we've been able to find a way to regress that information based only on 2 parameters. One is the size of the element that we're putting in, which is a representation of the polarizability of that element, and the other is the charge on the oxygen atom connected to that element. So we find very good representation, as you can see from the blue bars, and this allows us then to make a map, shown on the left, of the radius of the center atom versus the charge on the oxygen, and the lines are constant activation energies. So we use the formula to generate the curves here, and then we put in not the experimental values, but the theoretical values that we've calculated for tin, that's shown in the blue circle. Zirconium, the next best, is shown in the green circle. Things to the right are not active, so we neglect those. And we've made a prediction that if lead could be substituted in, it would have a significantly higher activity, the same mechanism, than tin does. So Mark, now the challenge is yours. Make us a lead beta, if it's possible, and we'll see whether we're right or we're wrong. So here's the conclusion for this element, that We've captured theoretically the effects of what happens on the isomerization. It does require a hydride shift. It also requires in the calculations that you take into effect the effects of confinement. So I've shown you 3 examples here, beginning with this set of illustrations that show you that not only the composition of the active center, but also its neighborhood matters. And that's the first bullet on this slide. And the second one is that none of this would have been possible without combining the results of experiments, the work of others, as well as our own, with theoretical studies that we've done. And finally, I'd like to acknowledge the people who did this work. Anton Leonard did the work on the oligomerization of propene in the nickel zeolite. Joe Gomes did the theoretical work that accompanied that. And Rajanda did the experimental work on butane cracking. Shama Sharada did the theoretical work. Mark Davis did the experimental work with his colleagues at Caltech, so nobody from my group that I can acknowledge, but Yipei Li did the theoretical work. And all of the theory was done in collaboration with my colleague from chemistry, Martin Head-Gordon. And those who supported the work are shown at the bottom. So with that, I'd like to conclude, and thank you again for this opportunity and for your attention. Thank you very much.
Thanks a lot, Alex. It's open for questions. We're going to do one of 2 things. Either come to the mic or raise your hand and I'll bring you a mic because I think it's important for the audience to hear clearly the question. Okay?
Alex, I just wonder whether you have calculated the effect of the silica-alumina ratio and how that affects the confinement that you already estimated.
Yes, we actually have done that. We haven't done the theory, we've done the experiments. They turn out to be hard experiments to do. But we've done this with MFI. We've gone from silicon to aluminum ratios of 140 down to 12 with one supplier. And we've measured the distribution of aluminum siting using the technique that Victor Lova and Dedicek developed in the Czech Republic of looking at the fluorescence from cobalt that you substitute in. And we see a systematic trend. We see systematic trends then in the distribution of the reactions and in the activity. And this we can trace back to changes, subtle changes in energetics, and even more noticeable changes in entropy effects. And there'll be a talk this afternoon by my student, Amber Janda, on that whole subject.
Alex, very nice talk. With respect, particularly to propylene oligomerization, at the temperatures you're running, you have a lot of water that's still there. I guess, and this possibility for all 3 cases, how have you taken into account the effect of water on the pore filling and on the electrostatics?
This is in the case of propene oligomerization?
The propene. I mean, your quadricite there, your X still holds on to water.
Oh, no. We've treated experimentally, we've treated the material to get rid of water. Because water actually will help in moving the nickel out of the hexagonal cages. There's published literature on that. No, these are completely water-free.
Anhydrous, okay. Yeah. One other related question. You looked at monovalent and divalent, but of course for the quadricite, it's really lanthanide series that preferred for the stabilization. So have you looked at the trivalent?
No, we haven't, but that would be a challenge to get enough of it in. With the trivalent, you start to have the problem of trivalents going in, compensating 2 aluminums, and then you have hydroxyl on them. So we didn't want to confuse matters. But we have the results I showed you experimentally, and what Joe Gomes is currently doing is exploring this theoretically. And the initial results are encouraging. They're showing the right trend that we articulate based on our intuition.
Thank you.
I have a short question on the propylene dimerization, because of course you mentioned that the resting state is an alkyl species, but if you start with a propylene, where does the extra proton come from?
Oh, there's a lengthy process which I didn't show of what happens in the activation. So at one point, one of the propylenes sheds a proton, And you have to have a methyl group or something larger. You can do this with butene, you can't do it with ethane. And that's left on the zeolite. And then at one point you form a diene, which is negatively charged, and eventually another propene displaces that. So it's kind of a one-time process to get to the resting state.
We did similar experiments on gallium exchange zeolite. You see similar effects if you do not have any protons. We did calculations and we ended up with explaining it with carbon ion chemistry, so negatively charged carbon.
Okay, we can talk about it. Yeah.
Excellent progress, Alex. There's a little detail. I'm not sure I buy your way of averaging the terminal and the secondary
The central cracking.
central thing. I mean, you should then have a weighted average including the dividend of the barriers. And this would mean that the step with the highest barrier has no relevance.
Yes, there are differences, as you saw in the calculations. There are slight differences in the barrier heights.
I mean, like 10 kcal, right?
No. Not between terminal and
Well, like 35 and 47 or something.
No. This is, you're thinking of dehydrogenation.
Yeah.
There's more than 10.
Yeah.
Between terminal and central dehydrogenation.
Yeah.
Not cracking.
Yeah,
there you're right. Yeah.
And there you did the averaging. And just taking into account only that you have 2 or 3 of the hydrogens.
Yeah. So what we're doing is we're just doing a Boltzmann averaging to get to the 42. Okay. Yeah,
This
so
was a Boltzmann average?
That was a Boltzmann average. It wasn't an arithmetic average. Don't worry. we would never do that. It was a Boltzmann average.
Let's thank Alex.
Okay, our next speaker is Dan Roscasco from Oklahoma.